In this video, I'd like to talk about some advanced linked lists. So some slightly more complex linked list structures that we can use that provide us some additional details, some additional affordances, make our lives a little bit easier with some of the operations that we want to do with linked lists. So first, let's remember what a linked list is. It's a series of nodes inside memory that may look something like this. Each node actually has two parts. So our node so class node would look something like this. Inside each node, there's the data that it holds, right? So this would be a linked list that's just holding integers because I just have an int field here for the data. And then this also holds a node pointer to the next element, right? Something like that. And then inside of our linked list class proper, the only thing the linked list itself would have would be a pointer like this to the head node. That's it. Just a pointer to the head node, right? So inside of our linked list class, it would look something like this. Linked list, right? And inside this, here's my node. And then there'd be one node pointer to the head node. That is the basic structure of a linked list. So there's two parts to these nodes, right? There's the data, 3, and there's the pointer to the next element, right? Now, linked lists are commonly drawn and pointers are commonly drawn in memory as like little arrows like this, but remember that these aren't actually arrows. Really, what these are fields in memory which have memory addresses in them. So this might be like 0xFF2AB2, and then this node would be at memory address 0xFF2AB2, right? That's really what's happening under the hood. But for ease of whiteboarding and diagramming, we always just sort of draw arrows instead. So our basic linked list might look something like this: 3, 4, 5, 6, right? And then the final node points to a null, right? So this is nothing, right? Instead of drawing an X there, I'll write the word null, right? Null, right? Now, null in C++ is 0. Actually, really what this should be is null PTR, right? Which is a null pointer. So when you're writing your code to implement a linked list, make sure you're using null PTR, which is essentially just the value of 0. So here's our very basic linked list. Now, one of the things about this, this is called a singly linked list, right? And I'm probably going to spell this wrong. It's called a singly linked list. So like singly. How do I spell that? Singly. Sure. Singly linked list, right? Which means that there's only a single link from all the nodes to the next nodes, and that's it, right? So one of the things that this allows us to do is we can only traverse in this direction. We can only go forward, right? We can't ever go backwards. So in the case that we do want to go backwards, right? And you can imagine times where you'd be like, say you're at this node and you're doing some operations and you're going to move the position of this thing in memory or do something else with it. And what you really need to update is the previous node's next pointer for some reason, right? And there'll be times when you may need to do this. Well, really what you want is this. You want a reference to the previous node, right? And that's called a doubly linked list. Doubly. It looks wrong. It's probably wrong. Someone check me. So a doubly linked list. So a doubly linked list looks something like this in memory, right? So here's our values: 3, 4, 5, 6, right? And the node class in this case would look something like this, where it has like the data inside of it, and then it has two pointers, a node for the next, and then a node pointer to the previous, right? And it looks like this. This is a doubly linked list. And this is pretty slick because it allows you to traverse backwards, right? You can traverse forwards and you can traverse backwards, right? Now, one real quick minor note is that traversing through a linked list is actually like not super great. a lot of the standard template libraries or a lot of the standard implementations of linked lists actually don't implement a subscript operator. And the reason why is because the subscript operator, I'll actually just write this out. So the subscript operator is actually big O of n, right? It's linear time. It has a linear time complexity. And the reason why is because the more data that we insert into our linked list here, the longer it takes for us to traverse through the entire thing, right? So if I say, give me the subscript at the third position, right? This is going to take 3 iterations. I got to start here at the head node. Then I got to go, okay, 1, 2, 3, right? Until I get to that 4th element. And now I know where, like, this is the element that I actually want to access with, subscript 3, right? So this is really slow. I mean, it's not really slow, but it's pretty slow, especially when you compare it to like the vector's subscript operator. Now, the vector subscript operator, remember that this one was sort of just dereferencing that pointer, plus we add in, I lost my thing. So we dereference our pointer, plus we add in that position that we want to access. And this works because the vector is in a contiguous block of memory. We have a pointer here, P, to the very beginning of that block of memory. We just need to hop over. We just need to move positions in memory, and we know exactly where it is. This is a constant time operation, right, which is big O of 1. That's essentially as fast as you can get. It's essentially just like saying int I equals 0, right? That is a constant time operation. So is this. That's the fastest you can essentially get. So subscript operators in a vector are much, 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 much faster. And they're kind of discouraged with linked lists. Linked lists is great for inserting and removing elements because we don't have to do all the shift operations that the vector has to do when it's moving around data in memory. But linked lists are slow when it comes to the subscript operator, right? Now, imagine the scenario where you want to insert a new element here, right? Let's see. Imagine the scenario where we want to insert a new element, and we want it to actually look something like this, right? We may do something where we sort of like traverse up to this element here, and then we say, okay, we're at the point where we want to insert before this. And now we need to somehow get back here so I can update this next pointer, right? That is where the doubly linked list comes in great. The doubly linked list, if you have traversed up to this position here, 5, it's really easy. You can just go backwards, right? So you could update this next pointer to point to something else. You can very quickly like move backwards a couple spaces or move forwards, right? It's easy to go both ways. You can traverse forwards and you can traverse backwards, unlike in the singly linked list where you can only traverse in the forward direction. So it makes some of the algorithms easier. This is a doubly linked list. Another type of linked list I want to talk about is a circular linked list or a circularly linked list. A circular linked list, essentially, and a note on this doubly linked list is that like the next pointer here is equal to null, and the previous pointer here is equal to null, right? Similar to this one up here, similar to this one, the singular linked list, where like the pointers that are on either end or at the very end is a null pointer. Well, down here, the pointers on either end are null pointers as well. It lets you know when you've reached the end. Like if you're iterating through this thing looking for an element and you get to the null pointer, you've reached the end. The element you're looking for does not exist, right? Or you're going too far. So a circular linked list is another pretty neat one. So let's start with the idea of the doubly linked list. 3, 4, 5, 6. Now let's imagine this scenario, and we have something that looks like this, right, with our next and our previous pointers. Now imagine this scenario, and this is null, and this is null, right? Let's imagine the scenario where we want to insert an element at the very end. Well, how do we do that? We have our head pointer here, right? This is where our linked list is keeping track of the actual class itself. And when we want to access the element at the very end, we would need to iterate through this entire thing. Okay, let's keep looping, loop through, until we get to the element that has the null pointer. Excellent. Now we can do the actual operations. Iterating through this thing, that was already big O of n. That was linear time, just to traverse through the entire list, right? This thing takes longer the more data that's in it. If there's 100 elements in here, it's going to take you 100 iterations to get to the very end. If there's 1,000,000 elements, it's going to take you 1,000,000 iterations to get to the very end. So inserting a piece of data at the very end of a doubly linked list is a big O of n, or a linear time operation, because you have to traverse to the end, right? Well, that's kind of a pain in the butt. And just to finish the statement, when you get to the very end, you create your new node. You'd say, okay, well, update the next pointer, update the previous pointer, add my new element here, whatever the value is, and then set this next pointer equal to null, and you've inserted at the very end. Okay, pretty straightforward there, right? Well, a circular linked list takes advantage of this pointer and uses it for something good, right? Or uses it for something interesting. What a circular linked list does is essentially says, you know what, why don't we take the next pointer at the very end and let's point it at the very first node. And then let's take the previous pointer at the very beginning and point it at the very last node. Now, if we want to insert something at the end, how long does that take? Well, previously, it was a linear time operation because it had to iterate through each one of the elements. Well, now we can take a look at our head node, look at the previous node, right? Which is just it. That's a constant time operation. We knew where the head node was, and we just say head node.previous, and we're there. Boom. We know exactly where it is. There was no iteration here, no searching, nothing, no loops. And now we're at the end. Okay, well, create our new node, right? We need to update our pointers. We update the next pointer. We update the previous pointer on the final node. We set the next pointer at the end node back to the very beginning. And then we set the previous pointer at the beginning node back to the front, right? Those are all constant time operations. We have references to the previous node, to the next node, to the first node, to the last node, right? We have all this data. And then we insert our new data here, right? Using a circularly linked list to insert at the very end actually becomes big O1, constant time to insert at the end. Right? And you might be able to think of other useful ways to use these next and previous pointers that are that happen with the circularly linked list. So typically, when you're building these things for the first time, you typically explore the standard singly linked lists, right? But most of the implementations in the standard template library that you'll find in C++ or in C# are actually a doubly linked list or either a doubly linked list or a circular doubly linked list, right? And there is also the idea of like a circular singly linked list, which would essentially be a singly linked list that only has single pointers to the next element, and then instead of the null pointer at the end, it's pointing to the one at the very beginning, right? This allows you to loop through the data and like loop over your entire linked list over and over and over again if you ever want to do that. But it still doesn't allow you to loop backwards through your list, right? So the most complex version of the linked list is really this one, the circular linked list, because it allows you the forward and backward traversal, as well as the circular traversal to go in either direction.